Professor Shekhar Mudu from Indian Institute of Science, Bangalore, Professor Vimal Mishra from IIT Gandhinagar, Dr. Sanskriti Menon from CEE Pune, and Mr. Ravindra Sevak from Safe Water Network. Industry Connect events are jointly organized by Ministry of Science and Technology and Ministry of Earth Sciences. And this is for 53rd event in the series of iconic 75 Industry Connect events to showcase the achievements in variety of science and technology areas as part of Azadi Ka Amrit Mahotsav. There are multiple objectives of iConnect events, and it was inaugurated on 12th May 2022 by Honorable Minister Dr. Jitendra Singh. I'll briefly discuss about today's theme, climate change impacts and water, and later my partner, our co-host, Dr. Krishnan, will take over. Our focus today is on understanding impacts of climate change on water resources. Climate change directly affects hydrological cycle, leading to extreme weather events, unpredictable water availability, exacerbating water scarcity and contaminated water supplies. You might be aware that around 75% of natural disasters during 2001-2018 were water related, including droughts and flood. Only major event other than these water related events was, I think, COVID-19. I will close with one glaring example. You might have heard about this water treatment plants in Delhi, namely Sonia Vihar and Bhagirathi water treatment plants. They were either closed for some time or they were operated at reduced capacity. And this is because of glacier retreat which took place in Chamoli district of Uttarakhand. And the water was so turbid in right bank canal, which supplies water to Ganga. The turbidity was as high as 8,000 NTU. And you might be aware that drinking water standard for turbidity is 1 NTU. So this is fallout of, say, climate change, and this is the repercussion of climate change. And we thought that we should organize this event on this important topic. So with these few words, now I'll hand it over to Dr. Krishna to take it forward. Thank you very much.
Thank you very much, Dr. Pawan, for the very nice introduction. And first of all, I join Pawan in welcoming all the speakers and panelists. And thank you very much for accepting our invitation. And as rightly mentioned by Dr. Pawan in his introductory remarks, climate change is affecting the water cycle in many ways. And we are already seeing that in the form of heavy precipitation events and also droughts in many parts of the world. And this situation is projected to continue in the future as well. So it's going to become more variable. Precipitation is going to become more variable because of the increasing water vapor and increasing temperatures. And but it's going to affect differently in different parts of the world. And extreme events, already we are seeing the monsoon in July. June, the situation was very different. By July, things had transformed in the next 15 days or so. And many areas we are having floods, and still there are some parts of the country where situation is dry. So the impacts are very profound. And so today we decided to put up this event, inviting all the eminent speakers and panelists to discuss about the water cycle and how do we adapt, what are the changes that are going to happen, and what are the conservation strategies. So we really look forward to the talks from all these speakers and also the panel discussion. So with this, So with this, I once again I welcome you all. So today we have. So I'll briefly introduce these speakers. We have Professor Subhimal Ghosh, who's basically from professor at the IIT Bombay, and his expertise is in hydrology and modeling of the hydrological systems, climate change, monsoons. He has done extensive work. And we also have today Dr. Prasad Modak, Director of eConnect Knowledge Foundation. He works on sustainable development aspects even related to water. And we have Dr. Aditi Mukherjee, who was the principal researcher at the International Water Management Institute. She is also a coordinating lead author in the working group 2 on water adaptation, and also a synthesis. She's also an author in the synthesis report of the IPCC AR6. And we have Mr. Jasveer Singh, who's from the Sensit Out. So he's more into practical applications of how to use water in efficient ways for irrigation and other purposes. And we also have very eminent panelists, Professor Vimal Mishra from IIT Gandhinagar, who has done extensive work on hydrological modeling, climate change impacts on both surface water, groundwater, extreme events. So he's a very prolific publisher and a very good scientist. And we have Professor Shekhar Muddu from IAC Bangalore, who works on hydrology, groundwater, agrohydrology, satellite hydrology, urban hydrology. And we have Dr. Sanskriti Menon, who's the Senior Program Director at the Center for Environment Education. And she works on community and school-based environment education, urban transportation, wastewater management. And also she has been actively involved in the development of Pune Cycle Plan. And we have Mr. Ravindra Sevak, who's the country director for Safe Water Network. He's actively involved in the development of safe water for the country's requirement, and also various NGO activities. So with this very distinguished panel of panelists and speakers, we are very happy to begin this workshop. And with this, I welcome all of you. And so now I think we can start with the first talk by Professor Subhimal Ghosh. Yeah, Professor Subhimal, I think you can typically go for about 12 minutes or so, 12 to 15 minutes, and convey your message, key messages.
Yeah, sure. Just a minute. Let me share my slides.
Just for the benefit of audience, we will be having 4 presentations of 15 minutes duration each.
Yeah.
And once we finish these presentations, there'll be panel discussion with the panelists, and the speakers also will join as panelists.
Yeah.
Thanks.
Sure. Thank you. Thanks, Dr. Pawan. Sorry, I missed that.
Yeah. Shall I start?
Yeah.
Is it?
Yeah.
Is the slides visible in presentation mode?
Yeah, it's visible. Yeah.
Yeah. Yeah. Thank you, Dr. Krishnan, for giving me the opportunity, to talk about climate to water, one of the most important sector which is getting affected because of climate change, and this has been reported quite significantly in the in IPCC, all the working group reports, and that shows that we are really in need of understanding the impacts, as well as we need to really find out the solutions. Impact understanding we have been doing for quite some time, but what is important is now we need region specific and sector specific solutions, and this is the need of the hour. So what I'm trying to do today is that we are trying to show that why India needs India specific solution, India specific modeling techniques, and so on. So why it is so specific for this country, and why do you really need to go for a region specific solutions? If you are considering the food, energy, water in the changing scenario, this is a very, this is one of the grand challenge which I feel for this country, because our country is actually, there is a significant population growth, and this is actually growing very fast. And to meet the food demand and for the food security, we need to intensify our agricultural activities. But what's happening for agricultural activities, our water demand is increasing, and at the same time, there has been increase in temperature. But over the last 50 years, if you see that monsoon has been kind of weakened or kind of stable, so there has not been really an improvement in the availability. Rather, the availability has reduced, but and demands have increased. So of course, the farmers are going for more irrigation. They have to go, and this has resulted into a significant increase in irrigation over the last 30, 40 years and so on, even after the Green Revolution. But what has happened at the same time is that government has started giving a lot of subsidies for the irrigation, and that resulted into huge groundwater depletion, because Here the irrigation is not controlled, it's completely uncontrolled. In a Western country, there is a soil moisture monitor, and based on that, you can irrigate, you can stop when you need to stop, and so on. But here it's not like that. Whenever you have availability of electricity, whenever you have availability of pump, you just irrigate, and that's the way it's happening. So what is happening? There is a significant groundwater depletion. Even there has been a lot of things which are where the flood irrigation has been converted to drip irrigation. But when we started interacting with few of the farmers, we realized that even for drip irrigation also they are continuously irrigating it. So it's not really monitoring the soil moisture, when to stop the drip irrigation and so on. So most of the cases it's like that, because farmers are poor, and then they do not many of them are below poverty line and so on. So they do not have really money to take care of these irrigation technology applications, etc. And what is happening at the same time, your irrigation cost is increasing, your energy is increasing. So even if government subsidize it, somehow it will be reflected in the tax and other things. So your crop price is increasing, and it's again affecting the food security, mostly for the vulnerable people who are poor people, and they are actually suffering from starvation and so on. So it's a huge challenge. It's not just a challenge for water, but it's a challenge for food security, it's a challenge for energy security and so on. It's a major challenge. And of course, there has been a significant depletion of groundwater. Of course, Bimal has done a lot of work on this. So that shows that groundwater has been depleting at certain locations in the Ganga basin. And these are the locations where, if you check the crop practices, etc., you'll find they are mostly irrigation dominated paddy fields. So irrigation dominated and paddy fields, these are two major things which is a typical Indian scenario, where there is uncontrolled irrigation and there is paddy field. So I'm stressing on both the things. I'll tell you why. So now, if you consider the major crop practices, what I was trying to say is that if you're considering the as a part of Indo-Gangetic basin, you'll find that majority of the irrigated crop is paddy crop. And for paddy, the things are entirely different. If you pick up any kind of hydrologic model which has been developed by the Western countries, what is happening is that most of the models consider either maize or soybean as their crop. So they do not really consider ponded condition of paddy. And the irrigation is when the soil moisture goes below certain amount, the irrigation starts and stops when the soil moisture reaches a certain non-stress. Reaches a some sort of a, not really field capacity, so slightly below field capacity and so on. So that's the way normally the irrigation works. But in India, what's happening? It's the uncontrolled irrigation and the paddy condition, which is not really considered properly in the state of the art hydrological model. So what we tried to do is that this is what which was a mammoth task, but one of my students, Jisha Joseph, has shown the courage to really start working on this, on really implementing a paddy formulation into the VIC model. So she has developed her own code, and she has included into the VIC 5, the latest version of the VIC model. And also at the same time, she has developed the irrigation, which is a flood irrigation, then drip irrigation, and these irrigations and intermittent irrigation. That means it's like the farmers normally follow every week Monday they irrigate. There are certain farmers. Some farmers, they just irrigate whenever they get water. So some sort of these things which has been considered. And India specific crops are also considered, and then there are Indian agricultural census, from which the typical water use has been considered, and based on that, these experiments were started, where there is one which is no irrigation, the second one is VIC with flood irrigation, VIC IRR, then VIC with drip irrigation, VIC with intermediate irrigation, and so on. So this thing, intermittent irrigation, so this is the way the framework was. And this was a very challenging task, because you have to really change the energy balance and water balance. When you are doing it for paddy formulation, what is happening is your energy balance gets changed because of the evapotranspiration from the ponded surface. So we have to do, I'm not going into the details of the mathematics, but this was a complex thing which we finally do. And then, when we started comparing it, the funny part is that we do not also have a data for a good validation. And then let's say if you pick up one of the data from Modi City, it is underestimating. And if you pick up one of the more data like GLIM ET, that will get another problem, because finally it's a merged model and observed data, and that model again considers the Western practices of irrigation and Western practices of crop and so on. So validation is a challenge, but at least the correct science should come out. That's the most important part. And then we check the sensitivity, and of course we have found what is expected, that flood irrigation results into more soil moisture and so on. So these are kind of expected results, but at least the model is working. So then, then the second thing what started is that we know that Professor Muddu Shekhar is there. So Professor Shekhar's team has developed a very nice model, which is the AMBAS model, and Professor Shekhar's team and BGS has developed VCAMBAS. So in the VCAMBAS, we have incorporated our irrigation module and the paddy formulation and trying to find out what's happening. So we have checked, we have applied again for the IGP region, and we have checked for the few regions. The first region is the region 1. We are talking about mostly the Punjab and Haryana region. The region 2 is Uttar Pradesh and Bihar region, and third region is it is not, I mean, this is some sort of western region. So what we have found is that for region 1, of course, if you just use a control run, it's not working, but with a VCAMBAS, it's doing well, but it's overestimating the groundwater depletion. For region 2, it's working very well. It's, I mean, exact ups and downs, it's unable to capture, but at least it's capturing. And the good thing about this model is that across boundary, across grid, water flow in the groundwater, that has been considered. And then region 3, of course, it's matching. So then, what we wanted to see is that what are the differences between flood and drip irrigation? Because there has been a debate over a large region, does flood irrigation really improves the case or not? So what we have found is that over Punjab and Haryana, of course, drip irrigation really improves, but a significant improvement was not found over the Uttar Pradesh and Bihar region because of non-paddy crop, one of the thing. Because for paddy crop, in any case, you are stopping the infiltration, but non-paddy crop, it's a different thing. Even for flood irrigation also, their infiltration increases because much of the water again goes back. So the improvements are not very significant, and that's what we have got. And yeah, I hope I am on time. So then the third thing is that what are the solutions? So because if we keep on talking about the problems, so I'm just quoting one of the quote by the Nobel laureate Professor Abhijit Banerjee in his Poor Economics book, where he has said that if you keep on talking about problems without giving solution, that means you are paralyzing the system rather than adding anything to the system. So considering that, we are thinking that how to really come up with solutions. And what I have understood is that providing a solution and working with the stakeholders and working with the farmers is not really a very easy task. I mean, over the last 2-3 years, I'm trying to do it, and I'm finding is that, and this is the occasion where I'm showing my huge respect to those who are actually working with the farmers on the field rather than just doing our own work within the lab. So who may not get much of the visibility. So this is one of the work which is started doing with some of the farmers of some farmers of Nasik district, where these farmers are actually getting IMD advisories. But when I asked them, they said that they know it's very good, but they do not know how to really use it. And these are essentially the rich farmers. And what these farmers, they have even soil moisture sensors on their field, but they want that, let's say tomorrow if I irrigate this much amount, for next 7 days I do not have to irrigate, because water arrangement is also a challenging task. So so then we started talking to them, and we said that we have extended weather forecast, so 3 to 7 days you will get very nicely, because for next 2 days they are not really very interested. They are thinking of a span of 3 to 7 days. Then extended range for 2 to 4 weeks. We have explained them, but they said that how can we we have our own bucket model, can you really incorporate that? So then we started thinking, and we found that let us do something very simple, because it's applying at a we have to do something which is applicable at a 50 meter by 50 meter farm, and we have to think in a different way. So what we started doing is that we have first doing a conditional distribution. So given a weather forecast, what is the rainfall distribution, we have generated a huge number of samples. And then what we did, we have developed an optimization model where a Monte Carlo simulation is going inside, and decision variables are irrigation water applications with the constraints, with a stochastic constraint that tells us that root zone soil moisture is less than a soil moisture threshold, with a probability, say alpha, which can be 95%, 90%, 80%, it depends on the farmers. And that will give you the optimized irrigation. So I'm not showing the results directly because in the interest of time, but we have shown that the 10 to 30% of the water can be saved if you just use weather forecast with the soil moisture sensor. So let the soil moisture sensor be there. At the same time, if you start adding weather forecast, and if you plan for irrigating every week, let's say on Monday every week, then you are actually saving 10 to 30% of the water compared to their practices what they are actually following now. And we patented this, and we published in WR and so on. Adrija, my student, did that. But when the farmers found it's really useful, they said that how can we really make arrangements? Because the second challenge what they face is that, let's say after 2 weeks I have to irrigate this much. We have to make the arrangements at least 1 week in advance or 1.5 week in advance, because sometimes water may not come. So then we have considered one of the another Ministry of Earth Science product, which is extended range predictions. So we have considered the extended range predictions, and then what we did, we have used the weather generator to generate multiple more ensembles. So around 1,000 ensembles we generated from the smaller number of ensembles which are there. And then again, you have used the farm scale eco-hydrological model. So a little bit of, out of the box thinking, we are just adding and then we are checking what is happening. And then again, with the probabilistic constraint, we have just get the optimal irrigation water management plan for 3 weeks. So remember, this is for water arrangements. So today I am arranging water. Today I'll start arranging water, what I'll be applying after 14 days. On 14th day, when you'll be applying, then we'll be following weather forecast. But today I'm just making the arrangements. And we found that even that is also working. Even 14 days in advance, you can, if you follow just extended range prediction, that is also saving water without any loss in the yield. So that shows that our weather forecast and extended range predictions have huge potential in saving water if you can use them wisely for the farm scale, and we can really develop tools for the farmers. That's the important part. We have to develop tools for the farmers, and there is a huge gap. We have to do that. Then coming to my last slide, let's say now if you have to do it over a large region, and this is what is very important, and you cannot expect, every region will have a sensor and so on. And if you consider a satellite product, that has a huge footprint, that doesn't really help the farmers who are actually working at a farm scale. So, so a typical case would be like this. The different farms will have different kind of soil properties, different kind of crops, and also, some of them will have sensors, some of them may not have. So the idea here is that, can we really use IoT and IoE kind of solutions where you will have sensors, you will have drone kind of, I mean, of course, we have to think of the cost also. We have to use the satellite measurement, merge all of them, and then come up with soil moisture map. From there, develop an optimization model and provide advisories to the farmers, which is a long way to go. But this is which is really, really needed now if we really make our agricultural practices sustainable. And of course, the second thing is the selection of crop types, which I'm not really covering today, but that is also another important thing. So these two are, are a few of many steps that are needed to really save water and solve and making our agricultural practices sustainable. And of course, this has to reach the most vulnerable group of the farmers. I'll just, before ending, I'll just give you an example. Recently, we are actually interacting with the farmers of Satara district. Satara district is in Maharashtra, which is having a very typical climate pattern. In the western side, we have 6,000 mm of rain, which is in Mahabaleshwar, a very nice place to visit. And on the eastern side, there are talukas like Man and Khatao, where the rainfall is less than 600 mm. And those are the places where people are really suffering from dry conditions and agricultural activities are suffered. And the major problem is that from those regions, a lot of people have migrated. The male population have migrated to Mumbai and Pune for job. And the agricultural activities are run by older people, the vulnerable people, and poor people, and also the women. So they are most vulnerable to climate change. And, so we have to think in what way we can actually, and some of them are actually going for even sometimes sugarcane and something, which is absolutely not possible. So the idea here is that, how can you reach the most vulnerable people? How can you help them in reducing the vulnerability? Because you cannot really control on the hazard. At least for 20, 30 years, even if you stop the greenhouse gas emissions, the same condition will continue. But can we really reduce the vulnerability by socioeconomic intervention and technological interventions, so that finally, at the end of the day, by reducing the vulnerability, you can reduce the climate risk? And that should be the challenge, and that should be our, our job to really save people from the climate change impacts. Thank you.
Thank you very much, Professor Subhimal. That was an excellent presentation. Yeah, maybe we will take up the questions later. We can now move to the second speaker, Dr. Prasad Modak.
Thank you. Let me just share my screen first. Are you able to see the screen?
Yeah.
All right.
Yes, Professor. Yeah.
So this is just a short presentation on the water stress index. And this is a work which we did for a large corporate in India a few years ago. So this is not a very recent work. It's been done about 4 to 5 years back. But I just thought of giving you how we approached to create a water stress index map for the country. The corporate who asked us to prepare such a kind of a map was interested where could they do and or provide support from their CSR budgets to improve the water situation. And water was identified as the central theme of sponsoring from their CSR obligations. Their interest was that can there be some science used to guide where this corporate should direct their CSR efforts, especially to improve situation related to water. So this became a kind of a research activity with the corporate with an interest that how can they use the outcomes of this research for some kind of a prioritization or decision making in supporting activities in various areas of the country depending on the kind of water stress. The way we approached was we thought we will create a matrix to compute this index, and our interest was, rather I would say the corporate's interest was, if we could develop such a kind of a index both at the district level as well as going all the way to the tehsil level. So 600 plus districts we looked at, and as you know, each district will have several tehsils. So the approach was to first develop these water stress indices at the district level and then identify the hotspots and then descend down to those districts where there was a need to go at the level of a tehsil to calculate the water stress index. So it was a kind of a hierarchical approach. Now we set up calculation of the water stress index in terms of three buckets. First was the water quantity, and the second was water quality, and the third was uncertainty, which looked at the uncertainty due to climate change and disaster proneness. And all these three buckets then had to be detailed further in terms of indicators. And obviously, we had to look at authentic data. Whatever data we wanted to use, we wanted that to be uh, mainly coming from the government sources. And wherever directly the data was not available, we had to look at reliable proxies which we could use. The quantity looked at the water demand, unmet demand, if at all there, and the both surface and groundwater. Groundwater, we looked at the information on the how much to what extent is the safe yield. And then in the water quality, we picked up data on the water quality reported on the surface and groundwater. And then we looked at the disaster proneness in terms of floods and cyclones and droughts. And once we identified these three buckets, we further got into the details of each of these and wrote down under each of these buckets what kind of variables and data sources that we would like to bring in. So in some cases, we did have observations or data. In some cases, we had to write some sub-models to fill the data gaps and predict. And we looked at about 25 years of climate change related predictions that time to especially address the third bucket of the uncertainty. So under each, we started identifying the variables and we started describing the rationale, how we will interpret the data for every district, because first we began at the district level. So we looked at the water availability for meeting the demand, looking at the surface water, groundwater draft, stage of groundwater development, future availability of the groundwater. We had here some estimated overdraft areas predicted, and we brought all these together under the indicators on water quantity. Then same thing for then was water quality, where we again have had some sub indices in terms of pollution caused or estimated due to fertilizer use in the agriculture areas and urban areas, the sewage disposal, and so on and so forth. So each of these variables had several sub-models to do required estimation and get more details. So moving on, the third bucket on uncertainty, we had these variables on the climate, disaster proneness, droughts and floods, and in cyclones. So a lot of historical data got used in this process. Few variables, we made use of climate models in terms of the future changes expected. And then we decided to construct from all these variables, which are the, at the criteria level and then sub-criteria level, a family of weights had to be set to aggregate, normalize first and aggregate next. So we use analytical hierarchical process to arrive at the weight. So we had fairly good expert consultation from each of these for each of these buckets. And then we computed separately water quantity stress and water quality stress and uncertainty in terms of sub indices, and then aggregated them to come up with a water quality, water stress index. So all these weights, as I said, were established following typical AHP to get some robustness in assignment of the weights as much we could in terms of objectivity. And once we aggregated, then we came up with a water stress index. While we were working at that time, there was also work done by World Resources Institute, and many of you are familiar with the WRI maps. So we had a joint meeting between us and WRI just to figure out what were the similarities or common approach and what was not considered by us or what was not considered by WRI. So this discussion helped us to further strengthen the computation of the water stress index, and then we generated a national map. And this is just one illustration I'm showing. The several such maps got created, and we use quartiles to to put them into different categories or classes. And based on these computations, more drilling down was done at the tehsil level. So now you see here the district and tehsil on your right side, and again the water stress indices got computed. And then for the interventions, we prepared a library of interventions to address the hotspots, and depending on what was that variable which caused the high water stress index. So this was an approach to come up with, first was to identify hotspots and the focus areas where this particular corporate wanted to support anything to do with water conservation and groundwater development. And then we looked at which variables for that location were influencing the stress index. And that library was then used for planning the field visits and doing surveys, so that there was you can say, a bit of a science-based decision the corporate wanted to do in formulating their water-related CSR strategy. So it's a short presentation, but I just thought of sharing that with you today. Uh, since we did this 4 or 5 years back, and the corporate used it, now we are in the update stage at this point of time, and we would like to look at the changes, what was computed then and now. So it is something which is based on administrative boundaries, unlike WRI, which was based on river basins. We took this approach because the corporate's interest was going for implementation, and they found that they could work in the administrative boundaries better. It was hard for them to work on the classification on the basis of river basins. So I'll stop here, and we'll be happy in the panel to take questions.
Yeah.
So this is just an example how sometimes consulting companies like us, we get into some research, which is coming mainly from people interested in practice.
Yeah.
Thank you very much.
Yeah. Thanks a lot, Dr. Prasad Modak. That was a very nice and very useful presentation on the water stress index for administrative purposes and for the corporate sector to deal with this problem of water stress. Yeah, we'll take questions later on, sir. So we move to the next speaker, Dr. Aditi Mukherjee, please.
Thank you so much, Dr. Krishnan, and thanks to the previous speakers for excellent presentation. I'm now wondering if mine is quite fit for purpose. Do you see my screen?
No, not yet.
Not yet.
Yeah.
Now?
Now it's there. Yeah.
Yeah. Okay. Okay. So I am actually coming from perhaps a big picture one, where while we know that in this room the climate crisis is also water crisis, if we look at all these bigger documents like the COP documents, actually I was horrified to see that water is not mentioned even once in any of the Paris Agreement, Copenhagen before that, or for that matter, the recent doubling declaration, sorry, the Glasgow declaration. So I think this is something that we as a water community need to talk outside of the water community to also make sure that water is a part of that bigger agenda, because this bigger agenda often decides where those investments, climate investments, will go into. So much of my presentation is along those lines. As I said, climate crisis is also a water crisis. This is a water group, so I don't really need to go out of my way to explain this, but it is surprising how much you have to explain to the larger climate community that it is also about, like, climate crisis is really a water crisis. But I'll save that explanation from us because we already know this. The thing that I want to highlight is water is largely neglected in climate change decision making, internationally certainly to a very large extent, nationally too also to some extent. Why this is so is why we need to think of water in climate change is climate change, as you know, has led to changes in all the components of the hydrological cycle. Dr. Krishnan was the one of the coordinating lead authors of the Working Group 1 chapter. His chapter, and combined with the chapter that I had co-led, also came to similar conclusion. Resulting in impacts mostly negative in almost all sectors of the economy and the society. This totally applies to India, almost all of our sectors, particularly agriculture. And we are such an agriculturally dependent country that climate change is already affecting 60%, at least 60% of our population who are in agriculture, let alone the others who are also being affected indirectly. We also know that majority of the people in the global south, that's us, who are in the climate exposed occupations, are actually experiencing climate change through water. So the way our farmers experience climate change is really through floods and droughts. So for them, water is that crucial thing that stands between a successful crop year and a bad crop year. What we also found through a global review, my number 4 point is that most of those adaptation, given that much of the vulnerable people experience climate change through water, most of the adaptations are also in response to water related hazards. as much of 60% of the documented adaptation, by documented I mean published in peer-reviewed articles, which of course may be a small subset of actual adaptation going on in the field, because we know that a lot of the adaptation is autonomous, undertaken by maybe small NGOs, undertaken by people themselves or by private companies. They do not necessarily always end up as peer-reviewed articles. But whatever we have, about 2000 articles or so that we looked for the IPCC, we found that majority are water related. And what is completely ignored, and I think is very important given that today's meeting is around also industry connect, because a lot of the industry right now would be, a lot of the investments in the future will be going to mitigation measures. And India is doing quite well in terms of solar and all of those. But the thing is that mitigation often has a water footprint that we tend to ignore. So that's something to keep in mind because some of the mitigation carbon reduction measures may fail if water footprint is not taken into account. Just I'll briefly go through those 5 points. I'm conscious of the time deficit. So one is that all components of the hydrological cycle have been changed, particularly heavy precipitation, droughts, to some extent floods, and also melting of cryosphere are some of the major examples of how the water cycle has been intensified. Well, it's been a little less intensified in India because of the aerosol effect, but nonetheless globally we are seeing intensification of the hydrological cycle. So this is a figure from the Working Group 1 IPCC summary for policymaker. I find it a very useful figure. It's what she's showing is that we are already seeing observed changes in heavy precipitation. This is our South Asia region, where we have also seen increases along with a large part of the globe. And the places that are gray does not necessarily mean that increases have not happened. It just means that there isn't enough data or literature to show any trend. Similarly, when it comes to drought, again, this is from the Working Group 1 SPM. In India overall, and this is where I think other Professor Krishnan, Subhimal, and Professor Mishra and all of you can come in more, but there does not seem to be, there seem to be low agreement in the type of change. But again, this may be an artifact of the data itself, but we already know that the droughts have become more intense. Then for what we have unequivocal evidence in our region around glaciers are melting, and at the very beginning Professor Lapteshwar, he actually made a very good observation about the impact of that on the industry, for instance, turbid water and all that. So we know glaciers are melting in the Himalayas, and it's affecting not only economy and livelihoods, not only the material aspects, but also cultural aspects of the indigenous people who live there. I'll come briefly to that in a minute. This is one of my absolute favorite graph, which I used to use a lot when I was working at ECMO. So this is the northern side of the Mount Everest in the background. This was a picture in 1921, and if you keep your eyes at the same spot, you will see that the glacier in front has melted, and what we now have is a glacial lake. And we are also aware of a lot of these glacial lakes being a high-risk area with resulting in large disasters, including the 2015 one that had happened in the Indian Himalayas. So this is something that we find in Himalayas and is a huge threat to all of us. We also know that water cycle will continue to intensify. Again, a figure from the Working Group 1, and that will affect annual mean precipitation, but also soil moisture, and all these are absolutely important for agriculture and adaptation. And this is all in the background of the fact that approximately 4 billion people are already experiencing severe water scarcity for at least a month. This is a study published a couple of years ago. Here people, like, this is a map of all the water stress due to water scarcity, and this is not only physical water scarcity, some of it is also access related, and both climatic and non-climatic factors are responsible, and climate change is just going to exacerbate it. Coming to my second important point is all sectors of the economy and the society, especially in the global south, are feeling the negative impacts of climate change. And this is from our working group 2 chapter of water, where we had assessed the impact of climate change on the various sectors. And you can find negative means negative impacts. So agriculture for sure, negative impacts in pretty much all the areas, with some mixed impacts, but mostly both current as well as projected impacts are negative. Majority of the other impacts are also negative. The lines are a bit light because of low confidence in that evidence. So this shows that there is a need for more evidence generation of what has been actually the impact, more attribution kind of studies, because attribution is not so easy when you are going not only from the climatic variables, but to the sectoral impact. So I think this is where, but overall the studies, whatever we have, are showing negative impacts on pretty much all the sectors: agriculture, energy, health related, which is water, sanitation, hygiene, that is health sector, urban and municipal sector, as well as ecosystems. We are seeing large negative impacts of, negative impacts of climate change. I won't go through each of these numbers, but these are just some numbers showing what are the globally what we are seeing in agriculture. 3/4 of global harvested land experienced drought-related agricultural losses between 1983 to 2009. With production loss, similar, we have seen that energy generation drops down drastically in hydropower plants during drought years. I think Professor Vimal and his students also have papers around showing the drought-related, hydropower-related projections in Indian context, and particularly the Himalayan rivers are getting affected, etc. Then we show that the impacts are particularly being felt by women, poor farmers, indigenous people. This is also Professor Subhimal said in his presentation earlier. We are seeing the similar kind, and in the context of cryosphere melting, that is where many of the ethnic minorities and some of the very traditional people with traditional lifestyles live. And we found like a similar story emerging from the global picture around these impacts being felt mostly by these indigenous people, and their way and cultural way of lives are being affected severely. For example, this is a community that I worked briefly on the irrigation system in Ladakh. And if you see those ice caps at glaciers that we can't quite see, but those are the water is being transported all the way from there into these small valleys for their irrigated system. It's a century-old system with very intricate technical as well as social organization around this irrigation. Now, when these glaciers melt, the very basis for their economy and their lives and their culture collapses. And these are the communities who are most vulnerable and have not contributed to carbon emissions at all. So this is, I think, also brings in the climate justice aspect of that. Coming to my fourth point is, as I've already said, is water is central to adaptation. The work that we did during the IPCC one was an assessment of around 2,000 or so articles, and we found that 60% of all adaptation is occurring in response to water-related hazards. Those hazards are largely drought, precipitation variability, and extreme heat related is also important, but a lot of it also around inland flooding and inland floods. Soil erosion, groundwater. So these are the different adaptations that we looked at. Font may be a bit small, but improved cultivars, agronomic practices, changes in cropping pattern, on-farm irrigation, and we looked at around 16 major adaptation measures, and we looked at, based on the published literature, what were people adapting to. So we find that majority of the adaptation is happening due to floods and precipitation variability. So showing that those are important, these are the ways people face climate change. And a lot of the adaptation is also about water. If you look at on-farm irrigation and water management and water and soil moisture conservation, you can see that these are two very important ways in which farmers are adapting to climate change. We found evidence of adaptation happening almost everywhere, and more so in Africa and Asia. And we also found that majority of the adaptation is in the agriculture sector in global south, while in the global north, adaptation is in the urban sector in the context of flood preparedness, etc. I mean, obviously, as I said, the caveat being that while this is a big database of 2000 studies, it is still not comprehensive because so much of the adaptation happens, so much of the adaptation that happens in real life does not really get documented in the form of studies. This is, well, one of those more complex figures, so I won't go into very much detail, but what is really showing is that while we have evidence that adaptation has many benefits, some benefits could be around livelihood improvement, but we do not really know if any of these, the literature is not enough to tell us with any level of confidence whether adaptation is reducing vulnerability. I think that is a big question mark that we have, and hopefully the next assessment looks at it more carefully, or we as researchers produce more data. I mean, sometimes an adaptation seems to reduce vulnerability in the short term, but vulnerability may go up if they keep using the same. I mean, groundwater is a good example where, groundwater over extraction can reduce vulnerability in a short term, but then in the long term, people become even more vulnerable. So this is, I think, a big gap in our adaptation understanding. Is adaptation really reducing climate-related vulnerability? And the literature and my own understanding seems to say that we don't really know, and in some cases adaptation may also be leading to maladaptive outcomes, which is actually reducing vulnerability in the long term. So that's something we need to be very careful about. We also looked at the future effectiveness of adaptation. So in this, the literature is much less. So we had around 45 papers, again, a very complex, typical IPCC figure with a lot of complexity. But I would just say that what we have done is we have looked at the similar adaptation measures for which we had data points. And then if you look at the main message of this is that at the higher level, so if you look at the 1.5 degree, you are seeing a lot of blues here. That is adaptation. These adaptations in the rows are effective in reducing risk. But if you look at 4 degrees, again, compare 1.5 with 4, you're seeing those the blue bits are becoming very less, while what's increasing is these red bits. The red ones are residual risk. So even after adapting at a 4 degree world, most of these adaptations will not reduce risk. So what we are saying is that it's not as if we can keep endlessly adapting. That's not possible. I think our heat waves this time showed the limits to adaptations are already being reached. How does a wheat crop physiologically adapt to 50 degrees centigrade? It simply cannot. Even with irrigation, even with every agronomic practices in the world, there is a physiological limit to which a wheat crop can withstand. And similarly, there's a physiological limit to which a human body can withstand. So we are fast approaching those limits to adaptation. So this is the same point. We are showing that adaptation becomes less effective with more warming. So I think this is very important, given that we are also almost confirmed to cross 1.5 degree in a next decade or so, and impacts in a 1 degree world are already so severe. So I'm not trying to be a scaremonger here, but this is an absolute reality. We cannot endlessly depend on adaptation. Adaptation reaches limits quickly. Then my final point is around most mitigation, and this is where I think private sector have a huge role because of the investments that are going into mitigation in our context around solar, etc. But all of these can have high water footprint. I will give you 2 specific examples. One is around bioenergy crops. Thankfully, we are not doing all of the bioenergy crops. There was, I think, 10 years ago, a lot of enthusiasm about jatropha and use of wasteland, but we have to remember, in a populous country like India, no land is really wasteland. There is somebody depending on that land for livelihoods anyway. So some studies are showing that, well, bioenergy crops can fix our mitigation problem, but it will exacerbate our water problem. So it's also same true in our local context. Similarly, another example is of forestation, reforestation. When these are done in wrong places, they kind of mess up with our hydrological cycle, which I believe Professor Mishra and Professor Ghosh and all of you would know much better than I would. But there would be changes in local hydrology, etc. And in the context, I think one more specific Indian example which I can give, and that's the project I'm working on around solar irrigation pumps. We are trying to figure out if solar irrigation pumps are actually great. And I'm right now in Bangladesh working with farmers who have installed these pumps. And because the monsoons are so late this year, the diesel farmers have basically given up on their their crop. They are just saying that unless there's rain, we are not doing any of the monsoon paddy, and that will be a huge loss. While solar farmers are able to irrigate because solar is more affordable. But what we are also looking at, what would be the water impact of those mitigations. So with that, I just stop here by saying that water is important because of water cycle is changing. That's how people are experiencing climate change by and large. You go and talk to a farmer, that's how they experience climate change. Water is a part of the problem, but also a solution. And very importantly, when we are making these big mitigation investment decisions, we need water on the table. I'll stop there, and apologies if I took more time. Thank you so much. Yes.
Thank you very much, Dr. Mukherjee. That was a very,
Yes.
very useful presentation, very nice presentation. We will take up questions later on. We'll move to the next speaker.
Sorry, I don't know how to unshare my screen.
Um,
How do I?
I think if I share it, it will unshare yours, maybe.
Okay, good. Okay, thanks.
Yeah.
Thank you.
Yeah. Okay. Next, we invite Mr. Jasveer Singh to please go ahead with this talk. Yeah.
Yes, thank you, sir. Just sharing my screen here.
Aditi, you have to click on the share icon again and it will unshare. Yeah, thanks.
Okay, okay, yeah.
Let me know if my screen starts sharing.
Yeah. We are able to see this.
All right. Great. Thank you. So, hello, everyone. Very good morning to all of you. I'm Jasveer Singh. I am the founder and CEO of Agri-Tech or Climate Tech, more specifically water tech startup called Sense It Out. Today, I'm going to be speaking upon IoT, climate action, and sustainable farming in context of climate change and water. The previous speakers have very well established, the importance of water and the effects of climate change, and I think it also opens up a lot of collaborations that we can have between the government organizations, the private institutes or startups like ourselves, and taking it further. I think one of the most what I'll be doing is I'll be quickly giving you in the next couple of minutes the impacts, effects, and reasons behind this climate change, and then I'll move on to the, more specifically IoT-based solution that we have developed to optimize the water usage at farms. Okay. So although I know that all these things are known, but I'm just trying to give a context here. Okay, so let me just start by saying that it's no more a climate change. It has become a crisis, and it is becoming a catastrophe going further. Okay, so what are the effects that we are seeing is that there is flood, there is drought, there is hailstorms, there is cyclones, and there's no predictability around these things, and the temperatures are rising. There are high carbon emissions, there are wildfires. Then all this is leading to a huge impact on the health of the crops, and that is why they are becoming more vulnerable to pest and insect attacks. They are more being vulnerable to more diseases, and this is mostly because alongside so if you look at the dry regions, Marathwada or other dry regions, with high temperature that they face now, they are also getting a higher humidity sometimes. Okay, so mostly affects the of course it affects the cotton, soybean, the staple crops, etc. But it also affects severely the horticulture crops like pomegranate or grapes, where the farmers are these are more like high risk crops. Okay, so and then we are also seeing that there is a very irregular distribution of rainfall, and it has become more like binaries. Either it is having flood or it is having drought. So if you look at maybe if the average rainfalls were same, then but still the distribution is so uneven that in a month, in a couple of days, the entire month's rain comes down. Okay, Just the recent example, because I come from Pune. The Pune's dams were just, we were seeing a week or 10 days back, we were seeing that they were very low levels, and Pune was trying to cut down the water supply. But then now in 1 week, 10 days time, the Pune dams are completely full with the amount of rains that we have got. So this is the invariability that we are seeing. Okay, then what is its impact on agriculture? That the yields are going low. Sometimes it is low, and sometimes it is also being washed away. There is increased farmer distress. Overall, at a macro level, if we see that there is a very big insecurity issue. The inflation is there. There is loss of species, economical catastrophe, and sometimes even most times even loss of life. Okay, so, but if you go behind the reasons, I mean, there are multiple reasons. I'll more specifically talk about global warming because of the increasing temperatures of the sea levels. Sea levels are rising, melting. The glaciers are melting, and this is all leading to the changes in the current directions. We all know about the El Nino, La Nina effects, but these are now lasting longer. No, these are not something which have come recently. They are there from decades or centuries, but then they are lasting longer, and the the effects are also becoming extreme at this point of time because of global warming. Okay, if we talk about the facts and statistics, more specifically, water in India, I'll compare it with few more countries here. So India has 18% of world's population, but only 4% of the world's freshwater reserves. And out of the freshwater reserves that India uses 90% of it in agriculture. Okay, uh, the water efficiency in India is also very poor. Israel, for example, has about 80% of water efficiency. Now we have seen that India has in last 1 decade we have seen severe drought. Australia has been seeing this since 1950. Okay, so the solutions there are more advanced. If you go talk about irrigation, water conservation, increasing water efficiency, etc. So like we say, necessity is the mother of invention. So Australia has much higher water use efficiency. Israel has about 80% water which is recycled. Okay, so eventually what is happening is because we are not recycling, and there is very irregular distribution of the even freshwater reserves. So India is more dependent on groundwater resources, and thus they are depleting very fast. Also because of the high increase in temperatures, the water is which is being used is very heavily in agriculture, because of evaporation, because of leaching, because of mechanization. The water is running horizontally rather than vertically down. So yeah, that's most of the background that I wanted to give. But now let's move on to the solution part of things. At a very macro level, if we say that we'll need a lot of farmers to get regional level alerts alongside. I think Professor Subhimal Ghosh talked about it a bit. We are working on satellite based data collection, and alongside, like I think Professor Subhimal Ghosh already mentioned that uh, it is very difficult to just use satellite data and help out farmers. So we'll need ground based sensors and maybe drone based data. But what I believe is that for larger set of farmers, for the bottom of the pyramid farmers who cannot afford a lot of sensors, what we'll need to do is we'll need to collaborate the satellite data alongside a ground based sensor data, and we need to calibrate it and come up with a lot of solutions. It could be around soil moisture, when to irrigate, etc. It could be around vulnerability of pest or insect attack, or disease vulnerability, and maybe give more actionable insights. Like an example was taken about the Nasik farmers. The problem I have seen is that we have enough data. We can do a lot alongside also, but what we do not have is we are unable to give actionable insights more customized to that farmer's needs. I mean, if we if we know that a particular farmer is going to be in a harvest, uh, 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 going to harvest in next few days, if we know that there is a hailstorm going to come, can we just suggest the farmer that, maybe you can go for early harvest? So these are very specific to that, customized to the farmer's needs. But I think we'll need to go to that level to give solutions that are more helpful. Okay, and at a very micro level, we need to, manage water in advance. Prepare for drought or flood-like conditions. In flood, we can have, like we have seen farmers who are using perforated pipes. Very simple solution could be called as a jugaad, but perforated pipes underground. These suck out the water from there and throw it into the drainage. So the crops are not affected by over irrigation during floods. And for drought, systems like Sikka that we have built, these can be used. I'm just going to talk about it. It's a sensor-based IoT product we have built. So that is where I will, take you through now. So at Sense It Out, that's my startup. We are making irrigation management smarter, reliable, affordable, and efficient. Okay, so we looked at, like, Professor Subhimal Ghosh also mentioned this, that farmers, it's working with farmers is very difficult. And, to tell farmers and, extract things out of them, or make them to do certain things because they are doing certain practices. It is very difficult. So we studied the problem very well. Going meeting a lot of farmers. We actually met more than 5,000 farmers. I started this work in 2015. Okay, in 2017, I formally registered as a startup, but my research has been since last 7-8 years. So we looked at the existing farm practices. What we saw was that they were watering irregularly. Mostly flood-based irrigation, and that was leading to reduced yield. So if they irrigate mostly, once they irrigate, they will irrigate after 5-7 days or maybe in 2 weeks time. So at a very micro level, what the crop is seeing is that a very flood-like condition or like a very drought-like condition. Okay, so like we humans, we will drink water as per our needs. The crops also don't like giving water, so in a very discreet way. They need it as per the requirement, and it leads to huge water wastage, because water can the soil can absorb water only till its capacity, and beyond that it will only leach out. So if you have a glass of water, if you fill it up beyond certain level, it is going to overflow, right? So soil is like that glass of water. Okay, and if I just talk about 1 acre of land, in 1 acre of land, if only 1 inch of water table was seen after the water holding capacity, 1 inch of water table was seen by a farmer, and he stops irrigating, then it will lead to 1 lakh liter. That 1 inch is about 1 lakh liter of water over an acre of land, okay, which is waste. Okay, and imagine the millions of acres that we have and the billions of liters that we will be wasting every day, every single day. Okay, so what are the available solutions we looked at before building our solution? We looked at the available solutions. Drip irrigation. Earlier, with flood irrigation, 1 week or 2 weeks you were irrigating once. Now drip irrigation, every day you are irrigating half an hour, 1 hour, 2 hours. It is also leading to huge water wastage. In fact, one research in Rahuri University, Agriculture University in Maharashtra, it says that drip irrigation in some of the certain cases were 40% more than used water, 40% more than the flood irrigation. Okay, and other solutions I looked at was timer based automation. But even timer based is somewhere, the farmer is intervening with the decision system. So the solution was a sensor based automation system. But we looked at various solutions that were there. The reliable solutions we found were the soil moisture sensors coming from US, Europe, Israel, Australia. These were very reliable solutions, but these were very unaffordable from the Indian context. And the affordable solutions that we are seeing, the Chinese-based sensors, these were very unreliable. And one more thing, that irregular electricity availability was also affecting the system's operations when you go for sensor-based irrigation. So we came up with this solution called Sikka. Sikka is basically a sensor-based intelligent crop-centric automation. Okay, I'll just show you how it looks. So if you see at the farm, there is a moisture sensor that we have put, soil moisture sensor. It has multiple sensors below the soil surface and measure the soil moisture levels at the root zone depth. Okay, and this root zone depth may vary depending on the crop that we are using and the stage of the crop as well. That is why multiple sensors that we use help us identify the help us check the soil moisture levels at that particular zone where the root zone is there. And this sensors are wireless. They send wirelessly data of this dryness to a controller which may be about 2 kilometers away from the farm. Generally it is about 300 to 500 meter away, and this controller then operates the pump and the valves that lead to that particular farm. Okay, and when the root zone moisture level is reached, then it gives a signal back to the controller to turn it off. Now, apart from this, so this is a very simplistic view, but we also collaborate the data of the temperature, humidity, etc. To also estimate the evapotranspiration that is happening at the farm, and estimate in how many number of hours the next irrigation cycle is required. Okay, that helps in countering the electricity uh, unavailability or irregularity scenario. Okay, and this again connects with the mobile app where the farmer can monitor and also change parameters. Suppose the farmer wants to irrigate further, then the current soil moisture which levels that are there, so at the time when the pump is supposed to be triggered and at the time when the pump is supposed to be turned off, the time in the sense the soil moisture levels, okay, these can be adjusted. If these are kept far from each other, then the frequency of irrigation will be lower, and if they are kept closer to each other, so we generally set it depending on the soil. These are the sensors are calibrated as per the soil and given to the farmer, so it reduces then it reduces the frequency at which the so sometimes we have seen, I'll just give you one example. In capsicum crop at Fulton, which is a place close to Pune and Satara, we had a capsicum crop, 3 months crop. We had compared 1 acre of farmland where only the Sika sensors were installed and decision making was completely sensor based. Another was a similar drip irrigated plot, but their sensors were not installed, and the conventionally how traditionally farmer was irrigating, they continued. We saw that the farmer said that they will be irrigating daily about half an hour to 1 hour. So they did that, and approximately in 90 days, they were irrigating about 45 to 46 hours of irrigation they had provided. On the other hand, the Sikka had, because it was black cotton soil, heavy soil, very high water holding capacity. The Sikka turned on this was between October to December, 3 months time duration capsicum was grown, and during that time only 4 or 5 times the system, the Sikka sensors turned the irrigation on. So overall 3 to 4 hours of turning on the pump. Okay, and that led to huge water savings, but also led to increase in yields because optimal amount of water was given, over irrigation was reduced, the fungal infection in the root rot was avoided. Okay.
Mr. Jasveer, 3 minutes maximum.
Sure, I'm just done in a couple of minutes.
Okay.
Okay, so this is the Sikka architecture. Multiple farms can be integrated with the same controller. About 12 farms to be exact. So 12 sensors that can be integrated, 12 farms. So if anywhere it can cater between, if you are having complete automation, then it can go from say as low as 2 acres to as high as 60 acres if 5 acre of one farm is considered. And if you just use the sensors in a data logger mode where you don't go for automation, then you can even go for up to 100 hectares, that is about 200 to 50 acres of land that can be brought with a single system. So that is the capacity of the system that I'm trying to show. And all the walls can also be wirelessly triggered. So you don't need to change the pipeline structure that earlier farmers were facing a lot of difficulty in adopting automation, that we are seeing that they needed the pipeline structure to be changed and made centralized towards the controller, so that the controller can then use wired walls to turn it on. So that we have changed completely. Okay, quickly a bit of what modules we are using here. We have a main controller, we have a wireless sensor module, wireless valve controller, and a MySika mobile app. I'll just run through the photos of how they look like. On the left, the controller is there. This is placed close to the pump starter. On the right, there is a sensor module which has temperature, humidity, atmospheric temperature, humidity, soil temperature, sunlight sensor, and multiple soil moisture sensors. These are in-house built soil moisture sensors that we were made it look affordable, made it more affordable. And we have the app that also tells where at exactly at that depth what is the soil moisture level, so that the farmer need not worry, because he looks only at the top surface and irrigates. Okay, so we tell them, okay, below this soil surface at this level, this is the soil moisture level, and all those things. Okay, this is how the valve control looks like. The bottom, what you see, if I don't know if you can look at my cursor, but the bottom line is actually the normal pipeline structure valve, and on the top of it in parallel we have put a solenoid valve that is being controlled by this wireless valve controller. Now, this is all solar powered, so we don't need to carry wires anywhere. So what we get out of it is that we are saving 80% of water potentially as compared to drip irrigation. This is very dependent on what kind of farm practices they are doing at the farm, and potentially again depending on the farm practices, the yield can also improve by almost 2 times in certain cases, and similar amount of electricity savings as in sync with the water savings can be achieved. Okay, one just quick example here. In Chambli village in the Purandar Taluka of Pune, we had experimented. You can see on the left manual side, because the farmer was irrigating, he had said that he would irrigate 1 hour every day, but sometimes he would irrigate, sometimes he'll forget because he has other works. Sometimes he'll start the pump and will close the pump after 2-3 hours because he was busy with other work. So irregular irrigation, you can see on the left how it is affecting. On the right, you can see how with Sika there is consistent growth, and it resulted in the quality of the crop as well. On the left, you can see decolorization because of irregular irrigation. On the right, we were able to see. So earlier with good climatic conditions, all these things were not required, but with the changing climatic condition, irrigation is very important, as it gets evaporated, the water gets evaporated from the soil, and the crops need them and as per their need. So with that, I will close things. We were awarded a lot of grants to develop this product, and some of the accolades that we had got. Thank you. I think that's my time. Sorry if I overshot on the time.
Thanks a lot, Mr. Jasveer. That was very, very useful and helpful presentation. Yeah. Now we can take some questions. There are some questions on the chat box. Dr. Pavan, can I go ahead with the questions?
I think we can initiate panel discussion, and then as part of panel discussion, we can take these questions. Yeah, okay. Our panelists have been waiting here for a long time.
Oh, sorry. Okay. Let's go with yeah. So, Dr. Pavan, I think you can start moderating the panel discussions.
Yeah, thanks a lot. They are very, very important presentations. One common thing which I found in all the presentation is that the most vulnerable don't actually contribute to climate change, but they suffer a lot. And all the speakers talked about that. How can we provide solution to these most vulnerable population? So I think they were very interesting presentations right from the field, and Mr. Jasveer Singh talked about how can we make use of IoT-enabled devices to really lead to climate change adaptation. And similarly, Dr. Prasad Modak also talked about water stress indices and how can they be used for various purposes. So because we are already late, so we'll initiate this panel discussion. So we're like 4 panelists with us, Professor Sheikh Amudu, Professor Vimal Mishra, Dr. Sanskriti Menon, and Mr. Ramendra Sevak. So we have a list of questions available with us. So we'll start with Professor Shekhar. So I will hand it over to Dr. Krishnan to go ahead with asking question to Professor Mudu first. Dr. Krishnan? I think, okay, Dr. Krishna is away. So we'll
Yeah.
start with,
Yeah.
Dr. Krishna, are you back?
I'm
Yeah.
sorry.
Yeah,
Sorry,
no
I had
problem.
to just.
No problem. So you
So,
can go ahead and ask a
first,
question to
yeah,
Professor Shekhar.
Professor Shekhar Muddu. Yeah.
Hi, Professor
So
Krishnan.
namaste. Yeah. So we wanted to know about with the groundwater depletion that's happening in India, which we are seeing from the satellite. So we wanted to know your views, your thoughts. How is this? This is going to become a big issue for the water availability. See, we wanted to know your views, how to adapt, what are the whether there are possible mitigation strategies and so on. Yeah.
Thanks, Professor Krishnan. I hope I'm audible, no? Can you
Yeah.
hear me?
Yes, you're.
Yeah.
Yeah, Professor
Okay.
Shekhar, you're audible.
Thanks for the clarification. I think I heard all the earlier speakers very nicely articulated various aspects of water stresses coming from surface and groundwater in the country and the climate impacts. So going back to your query on groundwater, I think it's quite a variable across the country, as you can see. One is you have a monotonic declines in the northern part of India, whereas in the south, it will not be a monotonic because we're talking about hard rock aquifers where there is a kind of a decline for few years and an increase for few years, and that kind of a system prevails in the hard rock systems because people can't pump out the water very easily in these hard rocks, and the aquifers act asymmetrically as you pump the water. So the interesting part is that as the levels go down, the yields go down in the southern part of Indian system of groundwater. So what happens is that when the yields decline, in the well yield, I mean, as the water levels go down, which is not the case in the alluvial systems. So as the amount of water needed for a farm changes, so like adaptation of infrastructure like irrigation, etc., would also have to consider what is the kind of a yield one would likely to get. So for example, typically drip irrigation is being used to save some water, but it's not often the case. The saved water is reused back by the farmer to increase the farm size, for example, to irrigate. So this is called rebound effect. So I think one needs to look at issues such as these. No one is trying to save the water, kind of. So the saved water is being reused. So we need to probably work on people to look at how to save the water by using a technology and also use it year on year differently. I think the issue came out as what should be the crop choice. The crop choice cannot be the same. The farmers are themselves adapting to various crops depending on the economy, etc. There's no single crop like rice wheat system of the North India in the south. So one needs to look at it. Parallelly, also, if you want to look at the groundwater to be more sustainable, only looking at irrigation, you have more aspirants every year. You have more and more stakeholders are getting interested in adding themselves into the agricultural land. So some of our studies indicated that if you have a farm pond, you might do some buffering. But if you have a bore well with a farm pond and change the crop, sometimes there could be a losses to the farmer. So we're saying that as you are adding more investments and infrastructure, some infrastructure could also be a negative externality. So these are important. That means changing the crop by adding a farm pond and a bore well could also give you not a increase in income, but potentially cause a reduction in the income. So that means we need to look at aspects not dependent on irrigation alone. We need to look at another path where there has to be a non-irrigation path also for the farmers. For example, you can have a side-by-side rain-fed and irrigation crops blended in the farmlands. That means all the farm need not be irrigated. You can have all of these. Also, probably as it was touched upon by others, saying that the energy is also an important variable. One needs to look at how the water is being used with the variable power supply, depending on the crop needs, which season. All of these would change the amount of water demand side. and that could possibly produce improvement. So essentially, we need to target something like productivity and decreased water use on the denominator, increasing the water use efficiency. If the water use efficiency by increasing the crop production and evapotranspiration increase will not increase because both numerator and denominator are increasing. We need to find ways to follow this. These are some quick remarks.
Okay. Yeah. Thank you very much, Professor Shekhar Muddu. Next,
I think,
Dr. Pawan, you want to?
Dr. Krishna, we can go to Sanskriti. Sanskriti, yeah.
Okay.
You know, you work for community, you also work for children, and you heard that impact of climate change on water is inevitable. And you might have seen, say, many presentations. Fortunately, our speakers today were very articulate and converting the, say, complex mathematical formula to the language which common people also can understand. But further, how can you simplify climate change impacts on water and communicate to the community and particularly to children? Sanskriti, over to you.
Thanks, Pawan, and really I should thank all the presenters, and I think other communicators, my colleagues at the Center for Environment Education, we would really love to work with scientists like Dr. Aditi and Dr. Ghosh and the other speakers because of their very important and concerning findings, and to identify the stories. They have themselves referred to stories. They've also shown some images, but using these stories and images to illustrate the findings, and also using, as you said, Pawan, that using local phrases that people can understand. Now, there has been similarly studies on what kind of communication strategies to adopt. There is also concern about how to integrate it into school syllabi, etc. And studies with say the Climate Action Network South Asia, CANSA, and the Global Center for Adaptation, which C has also been involved in, they do show that people, especially young people, well, people have heard of climate change, but not much understanding of the causes, the impacts, and the adaptation needs and mitigation needs and possibilities. Young people want to be involved in climate action and climate governance, but they find very limited opportunities, and they also feel inadequately equipped for such participation. And same it is with teachers. We also did quite recently research with teachers about their ability to teach and include climate concepts into their teaching. Now, the thing is that, as many speakers have spoken also, Dr. Aditi said that the impacts are visible, and communication can certainly refer to these. The communication should build on the local experiences and examples. And certainly the increased variability and the uncertainty of the monsoons, the extreme events, etc. These are very much extreme heat, also very much lived experience, which forms a basis on which to start the climate conversation or to enhance the climate. But perhaps what is often not apparent are the system structures that increase the impact, or and we perhaps also need to especially highlight latent vulnerability. And again, like I think the example of increased flooding in Pune was spoken, but again, the built environment that is causing increased flash flooding, which exacerbates the the extreme events. I think again that is lived experience, but that needs to be referred to. And I think while society will continue to live with the climate change impacts, it is very important that we start also very much talking about the constraints that the systems are posing on our ability to adapt. And so it is not only the impact that we have to communicate, but also, because that becomes very disempowering, becomes scary, but we have to show side by side when we speak about impact, but we also have to show the methods and the approaches to adaptation. And I think it's certainly that it's very important that we include climate related content in school and college and formal education. But we must understand that till the 7th standard, for example, the basic concepts of weather and climate are taught. And the ability to comprehend climate change may not happen till the 6th, 7th standard. It needs to happen a little bit beyond. But teachers can actually start looking at what we call as metacognitive content. It is the ability of people, young children, to look at collaboration, to teamwork, the ability to express for critical thinking and systems thinking. These will be important abilities. We call these sustainability competences that you can start building from school. And then in high school and in college, the more complex content related to understanding climate change and, because it's a changing field, the ability to access information. So these are things which are important when we speak about the education communication aspects of climate action. And while it's good to think of what we will do in school syllabi or high school syllabi, work is required to be done now, and that young people, it's a very important demographic for India. We are a young country, and they are the ones that need to have a lot of access to information and be involved in the techniques and the strategies that are being worked out. So again, when communicating, often people have a tendency to go into campaign mode, or there's an over dependence on social media. So I would like to caution that if anybody wants to use social media, they should really look at which demographic it is reaching, because often it is largely urban male that is social media usage, the people who are on social media. And the more vulnerable, or the women, they probably do not have access to social media. So, while there is an importance for social media, let's not overplay that importance. And instead, what we have to really do is look at more engaged and thought through and longer term approaches of communication and planning change with local communities and local governments. So things, a communication strategy very much needs to be built into schemes and development programs such as the Jal Jeevan Mission. It certainly requires that scientists work closely with organizations like CE, and there are so many others, and facilitators that can create the appropriate, very local specific strategies, communication strategies, because as we heard, there is a difference. Like Satara example was given. So you cannot have a district level strategy which is common. You will need to have one for the higher rainfall area and another for the drought prone area or the drier area. And I think this ongoing communication approaches, as much as science and research is an ongoing activity, so is communication. It's not a one-time activity, but very much a part of an ongoing evolution of the change that needs to happen. Just I want to give a small example. In Pune, Aquadam has helped many of us civil society organizations to understand the nature of groundwater and groundwater dependence. And in turn, we are engaging then with residents associations, the municipal corporation. We also had like an internship program with students to actually monitor, well levels, and actually create this directory of dug wells in Pune. And that forms, the basis of a conversation, the attention to groundwater that needs to be paid, because that is again a latent thing that you can't see and you ignore it, whereas it should form a part of the strategy for water management. Likewise, there is some emerging systems research on the food water nexus in the Upper Bhima Basin, which Stanford University is leading, and the researchers are here in Pune this week sharing their findings. That is again showing the need for these basin level public deliberations and conversations, and engaging with what if scenarios. What if there is repeated years of drought? Also showing that the equity discussion which needs to be part of water management, and that needs to become, you can't just do that over just media. You will need to have longer term, maybe socio-political, economic approaches which are embedded into the communication strategies. So I just
Thanks,
feel that,
Sanskriti, thanks. We'll come back to you with.
no, I'm done also. Thanks.
Okay,
Yeah.
thank you. Over to you, Dr. Krishnan, for question to Professor Mishra.
Yeah, thank you, Dr. Pawan. Professor Vimal Mishra, we would like to know your views. Particularly, you have done a lot of work on the impact of climate change on the hydrology, and even on the groundwater, surface water in the Indian context. So we would like to know how this, because also you're looking at the forecasts, hydrological forecasts, and the extended range forecast, how it is affecting the different river basins. So, and also Professor Subhimal Ghosh made some point. He also covered this aspect in his presentation. So we would like to take, so how this weather forecast can be integrated with the hydrological applications for the on this subseasonal time scale, so that it can help the farming community and improving the irrigation practices. Your thoughts on this?
Yeah, so thank you everybody. Thank you, Dr. Krishnan, for this, organizing this very important event, and talks were wonderful by Subhimal, Dr. Mukherjee, Dr. Modak, and everybody. So, I mean, the question, let's say, what basically we are missing when we talk about climate change adaptation in context of water. So if you look at like agricultural research being done last 2-3 decades, there has been a lot of emphasis on improving the water use efficiency, especially through drips, through sensor network, through, through various programs. And that has started probably, if I'm not mistaken, 2 decades back. So 90s, it started this program. Then on-farm water management schemes came. And there are challenges. So still, if you see, the groundwater has been depleting the way it was. So we have not made any progress at large scale, basically. So why I'm highlighting this? Because farmers, their thinking, their priorities are much different than what we scientists feel, as mentioned by Subhimal also in his talk. So at large scale, making any intervention that can solve our water challenges becomes extremely important, and we need to learn how we can do this. So certainly I can say like this, improving water use efficiency has not helped in depletion of groundwater over the Indo-Gangetic Plain. If you look last 16 or 20 years of data, it has continuously depleting because of increased pumping, because of, crop choices and so on and so forth. So groundwater becomes, the basic fundamental adaptation measure when we go in climate change, because of various reasons, because of, additional heat that winter season or Rabi season is going to face, because irrigation is always a way to sort of adopt excessive heat. So the demands in agriculture are likely to increase. And now, given that the monsoon situation, certainly we cannot say that monsoon is strengthening or weakening in the entire country, but we can say one thing for sure, that the behavior of monsoon is extremely erratic. So you will see every now and then a drought, and 1 year drought can pose basically 10 to 15% higher groundwater withdrawal. That's what we have sort of shown in our work recently. So if we put all these problems together, where we are heading to? So given the importance of groundwater, without groundwater, adopting climate change would be extremely difficult in India, because surface water storage cannot be ensured year round, given the challenges of reservoirs, or how much area we need to devote to store water on the surface, and so on and so forth. So we need to think little bit differently, at least at regional or large scale. So first thing, I think we need to do the mapping of aquifer characteristics. And that is, I am aware some work very important is undergoing in the leadership of NGRI. So we need to know where are recharge zones, where is the potential of, groundwater recharge. Every now and then we see that floods, enormous water generated because of multi-day extreme rainfall, and we need to harness that potential in our favor, basically. This is not a good thing, experiencing extreme rainfall and floods, but if we can connect somehow, and that would only happen if we know aquifers very well and we know the recharge zones. So we have to sort of not rely only on the improving the agricultural efficiency, but we also need to sort of focus on groundwater recharge, decentralized groundwater recharge, centralized groundwater recharge at various levels, starting from farms to regional river basin scale and the floodplains and so on and so forth. So that is, that is the emphasis on how we can manage groundwater, because relying that every farmer will follow the drip irrigation or they will use the sensors is still very, very challenging. I'm sure there is a potential, but reaching to all the farmers, given that their challenges in terms of their income, their revenue, their farmland holding, and so on and so forth, is extremely difficult. So that is number one. Number two, regarding the context of how linking, weather forecast or sub-seasonal, meteorological forecast, we can help in adaptation, climate change adaptation. There is certainly a lot of value, basically, because the potential of these, if we link these forecasts to hydrological forecast, as shown by Subhimal, I mean, even at farm level, there is a potential to save water. And not only that, basically the reliability of these forecasts and the usability of these forecasts, because many times forecast is available, but farmers don't know how to use it or how to infer the forecast and make the decision. So many times we have the information with us, but the actionable information is missing. So people cannot take timely action, especially the farming community, and that makes a problem. Sub-seasonal forecast, I can say that there are good skills in terms of soil moisture, at least 2 weeks, which could be very, very important to tackle the excessive heat episodes in the non-monsoon season and the flash droughts during the non-monsoon season. And those warning systems we can provide to community. The third thing we need to do, sort of mapping of risk. Adaptation, we need very, very high quality information in terms of risk mapping, where we do have risk for groundwater depletion, or during drought, there may be the crisis of irrigation or drinking water. So we need to develop risk maps for all the water related, elements, be it floods, be it droughts, be it irrigation, water withdrawal, be it groundwater depletion, and so on and so forth. So that information should be ready for long-term sort of policy level, interventions that we can make. Last thing is, which is little bit working group one, and Dr. Krishnan, you are coordinating lead author, so you must be aware. Many a times the problem becomes when we have mismatch between the observations and the projections. And that is very well related to the water sector. So if you see the continuous decline of the monsoon season rainfall over the Indo-Gangetic Plain, a region which is highly fertile, productive, that produces majority or one very significant part of food in India. And when you at the same time, if you look at the projections, most of the projections don't or models don't capture that regional scale variability in terms of how much rain we are getting and are going to get. So then the credibility or confidence in terms of developing anything for that region, given in the context of climate change, for policymaker or for actions, adaptation related actions, becomes a huge challenge. So what we need to basically sort of have models that can capture somehow, I don't know how to solve that problem, but regional variability of that we have been seeing in observation. I know if you look at working group one, there are three factors that affect the water cycle over India. One is greenhouse gas emissions, that is increase the monsoon, strengthen the monsoon, aerosols over the northern India, suppress the monsoon, and the third one is human interventions related to land use change and irrigation. So given that the watershed we have very complex, we just need not to just solely rely on the GHG emission thing. We also need to take care of the human interventions and aerosols impacts to sort of fully understand that how the water cycle will change in the future in our country. With this, I will stop here. It's so nice to see all other, great talks by Subhimal and everybody else. So thank you so much, Dr. Krishna.
Yeah. Thanks a lot, Professor Vimal. That was very nice. We'll come back. Professor Dr. Pawan, can you go ahead with
Yeah.
Ravindra Singh?
Welcome, Raviji. Our apologies that you have to wait for a long time. Yeah, but nonetheless, I have a few questions for you. The first to begin with is because you already worked with corporate, now you are working with communities. So, Dr. Prasad Modak had talked about how science can be used in influencing decision, and one corporate had approached him to use science to find out where actually they can invest their money of CSR. So with this, I would like to ask you that how are corporates and industries addressing climate change impacts on water in their businesses? So Raviji,
Thank
over to
you. Thank you so much for inviting us, and you and Dr. Krishnan, we are grateful to you. I would like to divide my comments into two categories. One is industry or corporates, and another is drinking water challenges. Because in industry and corporates provide industry 25% and service sector provides 50% of the GDP. We need their sustenance for the country's well-being. Anyway, if an industry has to survive, they must have water. So the biggest risk we used to evaluate when we were in industry is the business continuation risk. And that came from water. Because if we do not get water, we would not be in a position to continue our operation or our complete functioning. So is the case with the huge sector, service sector, which is residing in Bangalore, Gurgaon, or anywhere. So we as nation have to provide for these water resources. That's one. Second, we also assisted the Ministry of Jal Shakti as well as Ministry of Housing and Urban Affairs in developing their Jal Jeevan Mission or Har Ghar Jal or Amrut 2.0. Here again, government is spending all of 6 lakh crores in providing the water access and water security. But where will the water come from, especially under the climate change issues? So the basic question which all of us are addressing is the availability and also the impact on water quality, and especially its impact on poor. So the entire nation is currently focusing on creating 75 water body rejuvenation in each district of the country, and hope that it would reduce some of the impacts of climate change. It would also help us recharge the water in the groundwater, because surface water has a habit of evaporating, getting contaminated by microbial thing. But the groundwater is the largest reservoir that we have, and that is free. And it can be reversed. As you have seen in Telangana in last couple of years,
Hello.
water tables have risen.
तुम्हाला 100 वर्ष आहे. आता मी ईमेल तुम्हाला पाठवतो तुम्हाला जीपीसीबीला about to get
Yeah, Dr. Prasad, if you can kindly mute yourself.
पाठवतोय एक वेगळी ईमेल पाठवतोय to
Dr. Prasad Modak, if you can.
Maybe the host can mute him. Maybe as host you can mute him.
तर ती separate ईमेल
Dr. Prasad, can you please mute?
मीटिंग आहे इथे 2 जण आमच्या ऑफिस मध्ये अटेंड करतात.
Okay.
Yes.
So
I told
we
you
are working
I was
with
told
the
that there
communities.
is no Zoom link available. Pooja.
Vijay, please go ahead. Dr. Prasad.
So we are working also with communities. We are assisting the government of Karnataka in managing their 18,500 water treatment plants. And we can say that our own experience of running 350, we say about 10% of these get affected by non-availability of water. And almost 70 or 80% of these have water quality issues, either one or the other. And we need to address those challenges, be it microbial challenges, be it chemical challenges. And these are increasing by the day. So as a nation, we got to work on climate change adaptation by having larger reservoirs, larger recharge, better treatment facilities. As you had mentioned, even in Delhi, the turbidity has gone up to 8,000 NTU. Now, obviously, nobody can drink that kind of water. So we need to have focus both on quantity and quality. The drinking water is less than 1%. But if we see the entire urban and the provisioning of homes, it could be less than 5%. But that 5% gets affected by 90 or 85% of agriculture use, and agriculture excessive use of fertilizers, pesticides, and livestock excreta runoffs, because that also affects a lot of water body quality, especially the surface water. So I think we need to work along with the educational institutions as well as scientific institutions like yours, CSIR and meteorological department, etc., so that we can project, we can store water for not only these cities, but also domestic use. Both MOJS and MAHUA are doing tremendous work in providing tap water access. But is the water available? How to make it available forever is the task that we are yet to invest in and plan for. So I'm happy to answer any other question that you may have, Doctor.
Yeah, thanks a lot. Yeah, Dr. Krishnan, we have a couple of questions from audience. So should we take that first? Because we are now almost at 12. We need to I say 12:05.
Yeah. Yeah, we can take up the questions now. Then we'll come back with some closing remarks and thank all the speakers and panelists. I think, and we'll just quickly summarize the assessment that came out from this iConnect event. Yeah. So some of the questions, would you?
I have one question. Yeah, Dr. Krishnan, I have a question for Mr. Jasbir Singh, because Dr. Prasad seems to be busy. So, Mr. Jasbir, are you there? Yeah. This is the question for you from one Dr. Nandu Sekhar. And he needs a bit of clarification, because you mentioned that almost 1 lakh liter of water is wasted from 1 acre of land, because you told that if you have 1 inch depth of water, then we are wasting almost 1 lakh liter of water. I think he means that because part of it will be there for say groundwater recharge, and some might contribute to surface water recharge. So how do you actually estimate this 1 lakh liter? So if you can kindly elaborate. Yeah.
Sure. So when you irrigate, actually, it's much more than 1 lakh liter, but it's an example, and I'll give you a very simple calculation for it. So once the water, whatever water goes down, and the soil gets completely hold off with water, initially before leaching, it starts building a water table on the surface. And this water table, when it reaches 1 inch, you have seen, घुटने तक knee deep water भी लोग ले लेते हैं. But if we talk about only 1 inch of water table on an acre of land, if you do that calculation of 1 acre multiplied by 1 inch is 1 lakh liter. So it's an example. It could be, if it is 1.5 feet, then you can expect about 10 lakh liter of water approximately.
Thanks. So Dr. Prasad, are you available? Dr. Prasad, I think he seems to be busy. So, yeah, if there is any question from our panelists to speaker or other way around, we can say 1 or 2 questions.
Yeah. No, I think there are no questions as such.
Basically, I wanted to ask Jasveer about the cost if we have to do it, because in India, everything we do is about cost. And similarly, you mentioned the pump location could be 2 kilometers away. So IoT signal you are sending using a SIM, or are you using some other methodology?
So we are using LoRa based technology to do local communication. So it can go up to even 8-10 kilometers, but 2 kilometers is that we have set at this moment, and in a line of sight setting. And without line of sight, it reduces a bit. From the main controller, which is there close to the pump, it has a SIM card, which then translates it. So it acts as a gateway and sends it on the internet where we can access it. Okay, about and the other thing about the cost. So this controller, which can control up to 60 acres of land, we estimate that. So at scale, when we go, we are a startup now, but at scale when we go, we estimate to deliver this in a cost of a smartphone. Now when I say smartphone, I know the second question would be smartphone bhi alag alag कीमत के आते हैं, but for a smaller farmer, उस तरीके का product will have divisions in the product जिसमें a lower cost and a higher cost. Some we will work with sensors, some will work without sensors. We are trying to find out models where if we can use if one farmer is using a sensor, another does not want to use a sensor, but can it use the sensor data to collaboratively use that system? वैसे भी
Yeah, collaboration can work. Like most of the larger equipment are shared among farmers.
Absolutely.
So the same thing you could do also.
Yes. So
congratulations and wishing you all the best.
Thank you so much. Yeah. So per acre of land, it can come down to, without sensors, 5,000, with sensors around 10 to 15,000.
Yeah, I have one, it's not a question, more of a suggestion to Mr. Jasveer, and also I would like to thank Mr. Ravindra Sevak also for very, very important inputs about this interaction between the research lab and the private sectors. Just for information to Jasveer Singh, maybe he may be aware of it. So at IITM, we are making some soil moisture measurements, both using what is known as the COSMOS, cosmic ray neutron measurements, and also ground-based sensors. This is for getting a field scale information about the soil moisture. And then we want to connect it to understanding how to use it for hydrological applications and agricultural applications, something which you are thinking. So maybe we would like to interact with you.
Absolutely.
Hopefully. So that will be really helpful. And but all the talks were in general very good, right from Dr. Aditi Mukherjee's talk on the challenges in adaptation because of the water issues. They are going to become very complex. And also Professor Subhimal Ghosh, who really set the stage and how the approaches they are using for addressing the water issues, even at the farming level. So, and use of the subseasonal forecast, how is interacting with the farmers for making decisions. And also there was very important presentations about the, just a minute, about the SICCA development of the sensor-based crop automation, which Ms. Jasveer talked about. So, and also Sanskriti Menon's inputs about the water has to be, the importance of water, especially in the education, how to inculcate the education about the about climate change right from school level, and the importance of having safe water. Both the quality and quantity of water industries are going to be very, very important, and we have to sustain them. And the issue of groundwater recharge, which was brought out by Professor Subhimal Ghosh, which he stressed in addition to increasing water use efficiency, which Professor Shekhar Muddu mentioned, I think, and also the importance of risk map, especially the water stress index, which was nicely brought out for the corporate sector, how to do it. So they have come out with this very, very informative map, which for the administrative purposes, how the corporates and the administration can interact. So I think overall, if I see the quality of presentations, and it was an excellent event, and I want to thank all the speakers and the panelists for making very, very important contributions, and also to Pavan, Dr. Pavan, for coordinating with in organizing this event, and to the Ministry of Environment, Ministry of Earth Sciences, and CSIR for this opportunity. And once again, I want to thank all the speakers and the panelists, and Dr. Pavan, if I have missed out something, and all the participants for participating in this important event. Dr. Pavan, I leave it to you now. Sorry.
Yeah, thanks a lot. In fact, we have bank of questions, but because of lack of time, we'll not be able to ask these questions right now, but we'll definitely be in touch with you. And our objective is that how should we keep ourselves connected and bring in other audience also. But there's a lot of interest by audience to connect with some of the speakers and panelists. So thanks once again. Dr. Prasad is back. So Dr. Prasad, before we close, there was a question from audience. So we want all the questions to be answered. The question was that you have shown this water stress maps, and in some tehsils you have shown those green spots, which clearly indicate zero water stress. So how these tehsils and districts actually had zero water stress? So that was the question.
Yeah. So, Pavan, it is not zero. It is the lowest of the quartile. It is not an absolute value of zero. It cannot be. There is always a stress. But there is the last quarter. So everything was in quartiles. So the green was representing the last quartile,
So
the lowest quartile.
Was it because of low water demand, or say more water availability?
Surplus water. Surplus water.
Okay. Yeah. Thanks a lot. Thanks. With this,
Thank
I think,
you.
Dr. Krishnan,
I think
we are Professor Mishra. I think.
Yeah, Vimal Mishra.
Yeah, I just have a quick question. I'm sorry to sort of have this question at the last moment to Dr. Modak. So thank you for nice work, but I wonder, like, the data set requirement at the Tehsil level or Taluk level for the stress index that you have developed is enormous, given that you have incorporated water quality and other indicators. So is there any source of all this data that you can share with us, or how this data was collected? I'm curious.
So, Bimal, what was done was we didn't do for all the tehsils. We used districts first to prioritize. So the interest of the corporate was only to those tehsils where the district itself was showing a very high stress level. So, because that would mean humongous data requirement, that was not possible. So, first approach was to select the high stress districts. Then those were shortlisted further by other than water criteria. And then we were commissioned to go and mine out the data for the tehsils. So that mining out needed that we had to go and do physical visits and look at the government records. All data points were not available in soft copies. So it really required hard work to go to the field in those offices. And because you'll appreciate we are under NDA, we are not in a position at the moment to share the data. We are going through update of that map now because it's more than 5 years and a new cycle of data is available. So at that point of time, the corporate is actually thinking as a public good to ask us to put this data sets available to anybody. That discussion is ongoing at the moment, and I'm confident that that will happen because they also are looking at this as a part of their corporate social responsibility to share the knowledge. So, Bimal, it will happen shortly.
Yeah, thank you. Thank you so much. Much appreciated. Thank you.
Yeah, thank you.
Thank you so much. Maybe we can have a group photo, all the lovers. Can we, Dr. Pavan, want to take a picture?
Do we need to smile, Dr. Krishnan?
Yeah. Yeah. How do you take the picture?
Just take a screenshot. Just take a screenshot.
Window button and print screen.
Window button and sorry. Maybe screen I'm not able to.
I have taken. I'll maybe share it with you.
Okay. Okay.
Also taken. Thanks a lot. Thanks everyone for your time, and it was very, very interesting to interact with you.
Yeah. Thanks a lot. Thanks a lot.
Thank you, everyone.
Thank you. Bye bye.
Thank you very much.
Namaskar.
Many thanks to everyone. Thank you, professors. Thank you, Dr. Pawan. Thank you.
Thanks, Dr. Kishan. I think it went on well. Yes.
It went off very well. Yeah.
Yes. Thank you.
Yeah. Finally. Okay. Bye.